All right, welcome back. So let's say you're given you're given an acceleration, it's given to you, and it's constant. Uh, so the acceleration is ax plus times I hat plus ay times j hat, and it's constant. All right, so let's say it is constant. So how are we going to so this is a constant. This is, let's say, 1, 2, 3, maybe 0, maybe it's negative 10. So it's just constant. So both are constant. So how am I going to find the position as a function of time? Well, the position will depend. The x position, the component of position in the x direction will depend on the component of acceleration in the x direction, and similarly for the y direction, you use the acceleration in the y direction. So let's say we're given ax, we're given ay, we're given vx initial. I put here vx initial, the x component of velocity initially, and we're given the y component of velocity initially. And we're given the position initially, and we're given in the x direction, and we're given the y position initially. So how do I find x as a function of t? Well, simple. X as a function of t, just how we did it before, was equal to x initial plus v initial in the x direction, vx initial, times the time, plus 1/2 of the acceleration in the x direction times the time squared. By simply integrating the acceleration twice to get the position, because acceleration is the second derivative of position, so when you integrate twice you get the position, and then you will get two arbitrary constants, and they are vx initial and x initial, and but we're given those values. They're arbitrary, but if you're given the initial velocity and initial position, you can determine those constants. And so this is x as a function of time. That's just how x depends on time. And y depends on time. Very similarly, it's y initial plus vy initial times the time plus 1/2 of the acceleration in the y direction times the time squared. Sometimes you see them combined as the follows. Just the vector r as a function of time will be r initial plus v initial times the time plus 1/2 of the acceleration vector times the time squared. Right? This is an equation of this is really two equations in there, because r has two components, an x and a y, and r initial is x initial plus y initial, I hat and j hat, and the v initial, the initial velocity, is vx initial I hat plus vy initial j hat, and then the acceleration itself is ax I hat plus ay j hat. So really this equation here has two equations hidden in it. So now we're going to focus on the subject of projectile motion. So projectile motion, and then we'll talk about circular motion. So projectile So for projectile motion, we're going to make the following assumption. There is no air resistance. The only force involved, I know we didn't talk about forces, so I should say the only acceleration involved is an acceleration in the downward direction, and that's the negative y direction. That's it. So that means the acceleration, which is equal to an x component in the I hat direction plus a y component in the j hat direction. This one is 0. There is no acceleration in the x direction. If I have my chalk here, if I let it drop, it will just drop straight. It doesn't go this way, and it doesn't go this way. Why? Because there is no acceleration this way, so it doesn't start to move this way. Remember, if you start with a velocity equal to 0, If there is no acceleration, the velocity will remain the same because the acceleration is the change in velocity over time. If the acceleration is zero, there is no change in velocity. However, if the acceleration is non-zero, the velocity will start to change. If the velocity starts to change only in the y direction, the x direction remains constant, it means there is no acceleration in the x direction. So this part is zero. And what is the acceleration in the y direction? Well, it's in the negative y direction, so it's negative g, j hat. Meaning the acceleration in the y direction is equal to negative g, which is negative 9.8, and it's meters per second squared. And remember, g is positive 9.8. The fact that it's downward, we already took care of it. Okay? So let's see what happens to our equations for this equation here. We will have, if you have projectile motion, then you will have x as a function of time will equal to x initial plus v initial in the x direction times the time plus 1/2 of the acceleration times time squared, the acceleration in the x direction. But that's zero. So that's it. That's all you have in the x direction. How about in the y direction? Put the y direction here. In the y direction, I'll write it in yellow. I will rewrite this equation here. It is y will equal to y initial plus v initial in the y direction times the time plus 1/2 of the acceleration in the y direction times the time squared. But the acceleration in the y direction is negative g, so it's minus 1/2 of g times the time squared. You might ask, why don't we replace g by just 9.8 and put 1/2 of 9.8 is 4.9? You can absolutely do that, assuming that g is 9.8. But we like to just leave it g as g, just in case, let's say g in the problem tells us it's actually, let's say they say assume it's 10, or maybe assume it's 9.7 something, or maybe it's 9.81. So let's just leave it as g. We like to work in simples. Okay, so, and then what's the velocity in the x direction? Velocity in the x direction would just be dx dt. Well, what is dx dt? It's the x initial, you take the derivative, that's a zero because x initial is a constant. It starts at some number. Derivative of time with respect to itself is the same. So the velocity in the x direction initially is the velocity in the x direction at all future times, because it says Vx at a later time is equal to Vx initial. That's not surprising because there is no acceleration in the x direction. Let's say if you started with the x velocity, this chalk is at rest. If the x velocity was zero, it will just start falling downward. It doesn't make progress in the x direction, this way or this way. And so it remains zero. If I throw the chalk this way, I give it some component of velocity in the x direction, the x velocity, whatever that component is, will remain the same. We'll do an example on those in a moment, or a couple of examples. How about the velocity in the y direction? Well, you take the derivative of y with respect to t, that's the velocity in the y direction. dy initial dt, that's a constant, so that's zero. You take the derivative of this with respect to t, vy initial, that's some number you started with, so that's a constant. So you take the derivative with respect to time, so the time goes away. So it's just vy initial. And then you take the derivative of this with respect to time, the 2 comes down, cancels the half, so it's just minus g times t, minus g times t. And then there is the third equation which says vy squared minus, if you eliminate t from here and replace it, you will get vy squared minus vy initial squared equals to minus 2g y final minus y initial. Compare it to the equations of kinematics that we looked at in chapter 2. For x, here, you would just get 0 equal to 0. Okay? It's not going to change. So we will get, all right, fine, that's that. So how do we use them? Well, let's do an example here. I'll do an example of a projectile in general. here's an example for projectile motion. Example. I throw a ball at x initial. I throw a ball here. Here's x, here's y. And I'm going to throw a ball this way, in this direction, initially. And the ball will just go and come back. And it will fall here. We call this the range of motion. So it falls at the same level. It starts, I'm choosing my origin here. So it starts here and then goes. So initially the ball is thrown in this direction. So it has some initial velocity, and this is an angle theta. So you have a velocity v initial. Okay. So the velocity will have two components, one in the x direction, one in the y direction. The x is the adjacent to this. So vx, I chose this. Let me put initial instead of 0. X initial will equal to v initial times the cosine of theta. You're given theta, right? So theta is given. So we're given this. We have it. And so plug in your favorite number here. Let's say 10 meters per second, and this one, let's say 70 degrees or 20 degrees. So these are known numbers. So we're given v initial, we're given theta, we're given x initial, we're given y initial, and we're given y final. Right? We're given y final. So vy initial will be, you multiply by the sign because the y initial is the opposite. Notice the velocity starts heading this way, but then it changes direction and then as it falls. So it's v initial times the sine of theta. X initial, notice it's 0, you start at the origin. Y initial, let me put here, x final is called the range of motion. It's given this symbol r here, r. We're trying to find that. I don't know what it is. And y final is the same as y initial because it starts at the ground and then goes and then falls on the ground again. So that's also 0. Right? So the question is, where does it fall? Where does it fall, given all these numbers? Well, I can go back to my equations here. In the x direction, I have this equation, and in the y direction, I have 3 equations. So I'm going to choose here, which one do I find? I don't know what Vy final is. I don't know what Vy final is. These involve Vy final and it involves the time, right? So that's 2 unknowns. That's 2 unknowns. So I don't know it. This one will give me Vy final minus Vy initial is 0, so it says this right-hand side is 0. So that means Vy squared minus Vy initial squared is equal to 0. That means Vy final will equal in magnitude to Vy initial. But I don't know for now. I know it will be heading down. It will equal to the negative of it. But let's leave that aside for now. So I'm not going to use this one because it involves Vy final and it involves the time. So I'm not going to use that. So I will use this equation because it will give me the time. So I'm going to use that equation. Once it gives me the time, I'm going to plug the time in here. All right? So I have that equation. It says y final, or y at a later time, will equal to y initial plus Vy initial times the time minus 1/2 of g times the time squared. And we said Vy final equals to Vy initial. In this case, I have both of them 0. But anyways, they cancel. As long as you start from one height and you fall to that same height, they're going to cancel. So I have 0 on the left side, and then Vy initial times the time minus 1/2 g times the time squared. I'm going to divide both sides by the time, because the time is not going to be 0. The time was 0 at the beginning. I want what time is it when it comes to here? So that's at a later time, so we're not dividing by 0. So I'm going to divide by t, and then move this to the other side. So I have 1/2 of g times t will equal to vy initial. So the time will equal to 2 vy initial over g, and so the time will equal to what? Vy initial was v initial times the sine of the angle. So it's 2 v initial times the sine of theta divided by g. That's the time it takes for it to fall. It leaves and then falls. So if you want to maximize the time of flight to make it stay in the air for as long as you can, well, you have no control over v initial, right? Let's say you throw something. I mean, your muscles can only throw an object at a certain speed, right? Some maximum. You don't have unlimited power. Or let's say you have a gun or something that you're shooting. And so v initial is given, it's fixed, it's limited. You're limited by the power of whatever. If it's your muscles, you're limited by your muscles or your practice. So this is limited. Gravity, you have no control over it. It's just, you're on planet Earth, so it's going on around here. It's going to be about 9.8. The only thing you can control is the angle. So if I throw it at an angle equal to 0, it will just fall off right there. So the time would be 0. It's just not going to be much. Because if theta is 0, if you throw it horizontally, it's right on the ground, so it's not going to go anywhere. To maximize it, you want the angle to be, the sine to be as large as possible. And remember, sine, the sine of an angle between 0 and 90 degrees, the sine is the maximum value for the sine is 1. And that happens when the angle is 90 degrees. So if your goal is for this to stay as long as possible in the air, then you throw it upward. But if you throw it upward, it will just come back on you. It's not going to make any progress in the x direction, because if you throw it up, it will just come down. There is no x component of velocity. And in fact, you can see that. If the angle is 90 degrees, cosine of 90 is 1, there is no progress in the x direction. So it will just go up and fall down. And so we're going to find the range, and then I'm going to ask, what angle will it make the range? At what angle is the range maximum? And you would not be surprised by the answer. You might already know it. So let's find the range. I know that x will equal to x initial plus vx initial times the time. I'm going to do that. I know that x will equal to x initial plus vx initial times the time. And so x will be, what's vx initial? That's 0 plus, right? Vx initial is 0. And then, I'm sorry, not Vx initial. X initial is 0. Vx initial is V initial cosine theta. So that's V initial times the cosine of theta times the time, but the time is 2V initial 2V initial sine theta over G. 2V initial sine theta over G. And so x, or the range of motion, how far will it be from where it started in the x direction, would be 2 v initial times v initial is v initial squared. So it would be 2 v initial squared. And then sine times cosine, sine theta, times the cosine of theta over the g. I'll just write the g here. And so, let me just write it again here. So x, the range, would just be what? First of all, from trigonometry, you know that 2 sine theta cosine theta is the double angle formula, and it's the sine of 2 theta. It's the sine of 2 theta. And then here I have v initial squared over g. That's the range. If you want to maximize it, you want to throw this thing, let's say you're one of those discus throwers, you want to throw it, at what angle should you throw it? So if you're going to throw it from this level and it goes back to the same level, this is the range. How do I maximize the range? Well, I have no control over V initial. That's my muscles, or the muzzle velocity from the spring gun or whatever that you're using. Gravity I have no control over. I can control the angle with which I throw. Now remember, the sine function is a function that's between +1 and -1. So the maximum magnitude for the sine is 1. And when is the sine equal to 1? The sine of a certain angle equal to 1 if what's inside the sine is 90 degrees. And so twice theta has to be 90 degrees, because if I put 90 degrees here, if this is 90 degrees, I get the maximum value for sine. So theta has to be twice theta is 90, so theta would be 45 degrees. So maximum range is when theta is equal to 45 degrees. And I want to re-emphasize this. This formula only applies if this is the starting point, if you throw an object and it lands at the same level. If you do this, if you throw an object from here and then it lands below, then the angle that maximizes the range is actually not 45 degrees. It would be, if this is lower, it would be slightly less, maybe 30 something degrees. So if you throw something from the ground and it lands on the ground, or it lands on the same level, if I throw it from a table and it lands on that same table, the maximum range would be 45. The range would be maximized if the angle is 45 degrees. All right. So here is another question. Here is the range. Here is 45. Let's say it lands here, right, at 45. And how about if I throw it at 45, let's say, plus 15 degrees, that's 60, right? 45 plus 15 degrees, that's 60. Versus if I throw it, let's say this is 60 degrees, 60 degrees. Versus when I throw it at, let's say, 45 minus 15 degrees, which is 30 degrees. If I throw it at 30 degrees. It turns out that if you add or subtract that same angle, you will get it will land at the same position. So if you take 45 and you add to it a 90-degree angle, I'm sorry, not a 90 degree. If you add to it an angle between 0 and 45, then it will be the same. So for example, because 45 plus 15 is equal to 60, and 45 minus 15 is equal to 30, then they will give you the same range. 30 and 60 will give you the same range. And if you do, let's say, 45 plus 10 degrees, that's 55, and 45 minus 10 degrees, that's 35. 35 and 55 will give you the same range. So how do I prove that? How do I show that, right? Well, let the angle be, so I want to show that 45 plus an angle phi, or 45 minus that same angle phi, will be the same range, right? So it will give me the same range. So like for example, 45 plus or minus an angle phi will give me the same range. How do I prove that? Well, that means I'm saying that if I take, the range is V initial squared over G times the sine of 2 theta. I'm saying that the sine of 2 theta, if I add 10 degrees or subtract 10 degrees from theta, the sine will give me the same number. So I want to show you that. So if theta is 45 and I'm going to add to it plus or minus phi, an angle phi, so the sine of twice of theta plus or minus phi. That's what I'm going to show you. That plus or minus phi, it will just give you exactly the same result. And theta here is 45. I'm going to take 45 and add to it maybe 10 degrees or subtract 10 degrees, and it should give me the same number. So let's see why. Let's multiply the 45 through, so I get the sine of 90 plus or minus 2 phi. And we will use trigonometry here. The sine of an angle, sine of something plus or minus something will be the sine times the cosine, and then plus the cosine times the sine. So it will look like this. The sine of 90 times the cosine of plus or minus 2p, and then plus the cosine of 90 times the sine of plus or minus 2 theta. Sorry, I'm squeezed here. And remember, the cosine of 90 is 0, so this whole thing will just be 0. The sine of 90, so I should have equal sign here, equal sign here, equal sign here. The sine of 90 is 1, so that goes away. And this will be the cosine of what? What's the cosine of plus 30, let's say? Well, it would be radical 3 over 2. And the cosine of negative 30 would also be positive radical 3 over 2. So the cosine is what we call an even function, meaning the cosine of negative phi is the same as the cosine of positive phi, right? Or the cosine of negative 2 phi will equal to the cosine of twice phi. So this is just the cosine of 2 phi. The plus or minus doesn't matter. So what we have proven here is that whether you add or subtract, you will get the same result, and the range will just be the same. Okay? So that was projectile motion. Okay. So my next problem will be talking about relative motion, and then I will talk about circular motion, and that's the end of the chapter. All right, I will see you in the next video for relative motion and then circular motion.